Hello, everyone. In this video, we will introduce Chapter 26, AVL trees. AVL tree is a special case of binary search tree. The search, insertion, and deletion time for a binary search tree is dependent on the height of the tree. In the worst case, it can be order of n. If a tree is perfectly balanced, that is a complete binary tree, its height is order of log n. Can we maintain a perfectly balanced tree? Yes, but it will be costly to do so. The compromise is to maintain a well-balanced tree. That's the heights of two subtrees for every node is about the same. AVL trees are well-balanced. AVL trees were invented by two Russian computer scientists. In an AVL tree, the difference between the heights of two subtrees for every node is 0 or 1. It can be shown that the maximum height of an AVL tree is order. Let's look at the example. In this binary search tree, 45, the balance factor is 0. Now, balance factor is defined as the height of the right subtree subtract the height of left subtree. In this case, there's nothing here, nothing here on the left, so this is 0. Now this node 5, for 55, the balance factor is -1 because the height of the right subtree subtract the height of the left is -1. Thus 60, the height of the right subtree is 1 more than the height of the left subtree. Therefore, this is +1. The balanced factor for every node, if it's 0, 1, or -1, then the entire tree is an AVL tree. Let's look at this animation for inserting, deleting, and searching elements. So let's first perform this insert 45. 45 would be inserted right here. Now, if you put 45 here, look, what is the balance factor of 25? It will be +2. So this right side will be 2 more higher than the left side. So this 25 is not balanced. We're going to perform a rotation to make it balanced. So this is what happens. You're going to see this 35 will be here, 25 will be on the left, and 45 will be on the right. So this is the result. Another insert, I'm going to insert to this 15. So when you insert 15, you put 15 right here. Now see what happens is the balance factor now. So this will be the problem here for the 50. the balance factor will be -2 because here is 2 less than this left side on the height. So you're going to perform a rotation at 50. And the result is you're going to have this 35 here, and then you make some adjustment, and you're going to put this, this is the one right here. You're going to make the adjustment and make other adjustment along the way. So let's look at this now. So this is 35 right here. All right, you can see that this is 45 is here. So there's additional adjustment needs to be made along the way. When you remove it, and you will have to perform the adjustment to make sure it's going to be rebalanced if it's not balanced. So you do it normally like you do for the binary search tree where you remove things, and then afterwards you're going to discover if the tree is balanced. If it's not balanced, so you're going to rebalance it. All right, so let's look at the ways to rebalance it. Rebalance the tree, we're going to perform the operations called rotation. So there are 4 cases for 4 types of rotations. And the first one is called AVL rotation. Is this the case? You identify a node A, which is not balanced. The balance factor is incorrect. It is not 0, 1, or -1. So it's +2 or -2. All right, so in this case is -2. It means it's left heavy. The left child of A, further, at least it's left heavy. So look, it's going to be -1 or 0. So this is the case, it's called AVL rotation. So you're going to perform a rotation, it's going to rotate it to the right. The way we're going to rotate it is this. So this T1 is the left subtree of B, and T2 is the right subtree of B. So when you rotate it, and you're going to put the B on the top, and A is going to be the right child of B. And then this T2 becomes the left child of A. And this is the L rotation. And similarly, the R rotation is the right heavy. So here is the A is +2, the balance factor. And the B, the balance factor is +1 or 0. So it's at least going to the leaning toward the right. So this is right heavy. And when you perform a rotation, you're going to rotate it to the left. So now B is here on the top, and A becomes the left child of B. And here, this T2 is now becoming the right subtree of A, performing the rotation. And there's 2 more. This is the left-right rotation. It is this. A is left heavy, but the left child B is the right heavy. It's going to right. So the way we're going to perform it is B, look here, is we're going to promote the C to the top, and B is on the left side of C, on the right, A is on the right side of C. And then make adjustment, now make this T3 to be on the left side of A. And this T2 is now on the right side of B. So everything is now balanced. And this is the RL rotation is right, left. It's for A, it's right heavy, but B is left heavy. So the way we're going to do it is put the C on the top, and A becomes the left child of C, and B becomes the right child of C. And then make additional adjustment is to move this T2 becoming the right subtree of A, and T3 becomes the left subtree of B. And now let's design this AVL tree class. We're going to put this AVL tree as a subtype of BST. This constructors, and now this is the created node. We're going to create the AVL node. So what is the AVL node? It's an extension of the tree node. So you have the element, you have left and right branch, and then you have this height. So the height is important. From the height, we can compute the balance fact to determine whether a node is balanced or not. And we're going to overwrite the insert method and delete method. And so these are all the private methods we're going to use to rebalance the tree. We'll compute the height and rebalance the tree. So this is here, and for this. So look, this is the AVL tree node. It's extension of the tree node. So the complete information now you can have for this AVL tree, its element is defined in the tree node, is accessible here in the AVL tree, and the height. And that's a new in the AVL tree node, and left and right is all inherited from the tree node. Let's look at this. How are you going to overwrite the insert method? You're going to perform the insert method just like for the binary search tree. And afterwards, we have to see if we have to rebalance the tree. So look at this. We have this new node is inserted into the binary search tree. And now along the chain all the way to the root, we're going to see which one is the problem, is unbalanced. So now this is the first one we discovered is unbalanced. It's right here. It's this is the A. And this is the parent of the A. So we're going to do some work here to readjust it. So the way we're going to readjust it is here. Look right here. Is so we have this A now identified. So for each node A in the past leading to the root, we're going to update and the height of A, and let parent of A denote the parent of A, and which is the next node in the past, or null if A is the root. We're going to check on this if this is not balanced. So we're going to balance this. Let's look at the balance factor of A. If it's a -2 or +2. If it's -2, so we're going to consider it's left heavy. So we're going to look at this left child of A. If it's leaning to the left, we're going to perform L rotation. Else, we're going to perform LR rotation. It's left and right heavy. If the balance factor is 2, it's right heavy. So A is right heavy, and the A's right child is leaning to the right. We're going to perform RR rotation. And otherwise, we're going to perform RL rotation. So this is how this is performed. Okay, let's take a break. We're going to examine this implementing rotations in the next video. Thank you for watching this video. See you on the next video.